Okay, so the next portion says you can solve rational equations, but make sure you check your solution. So remember, some numbers could have made the original rational expression undefined. So there are numbers that make our rational expression undefined. So I don't know if we talked about this before, but basically, like when you have a rational expression like 5 over x squared minus 9 over x plus 3, 10 over x squared minus 5, like there are certain things that I can't plug in for 0 because it makes it undefined. So with 5 over x, what can I not plug in for? Sorry, I said for 0. What can I not plug in for x? Because I'll get 0 in the denominator. 0, right? How about the next one? What can I not plug in? I can't plug in negative 3. So I realized that x squared minus 9 over x plus 3 factors, right? And then you would remove that x plus 3. But in the original problem, you still can't plug in negative 3. It makes it undefined. Okay, if I was doing like a t-table or something, I would get undefined. Okay, so that's what it's talking about here. So sometimes, even though you get an answer, you want to check in the original just to make sure that it's okay. So there are a couple different ways to do these problems. So one thing that you could do is you could take the x minus 5 and you could multiply it to the other side. Okay, so look up here. You don't have to write this down, just pay attention. Okay, so if I do that, I would have x squared minus 25 equals 14 times x minus 5. And I would then multiply out. And I would get everything on one side. So I'd have x squared minus 14x. And then I'm going to add the 70 over. So I'd have plus 45. And then I factor. So I would factor into x minus 4, or not x minus 4, x minus 5 and x minus 9. So we would get two solutions. We would get 5 and 9. But if we went back to the original equation and we checked 5, so we plugged in 5 to the numerator, 5 to the denominator, do you guys see how you would have 25 minus 25, which is 0, over 5 minus 5, which is 0? Is 0 divided by 0 equal to 14? No, it's undefined, right? We don't know what 0 divided by 0 is. So 5 would be one of those extraneous solutions. So it would be extra. So that would not work. So then 9, if you try 9, you'd have 81 minus 25 over 4. So you'd have 56 over 4, which is 14. Okay, so that one would work. Okay, but there's an easier way to solving this problem. So does anybody kind of see what we would do here? Gloria, what do you think? Yeah, in this case, we could factor. So if we factor from the beginning, and we say, oh, I have x plus 5, and I have x minus 5, all over x minus 5. So go ahead and write this down now. Whoops, not equals 0, equals 14. Then when we do that, that x minus 5 cancels. And we're left with a super simple equation, x plus 5 is equal to 14. So we end up getting 9. That is our only solution. You can check 9. So just like I did before, check 9, you get 56 over 4, and that is equal to 14. So that one worked. It checked out. Okay, does that make sense? So it's easier to factor and eliminate the one that was going to be bad anyway, if possible. So on this next one, if I factor, I have x squared plus 3x minus 10. So I factor into x plus 5 and x minus 2, right? So my outer and inner combine to be that 3x. And then it's over x minus 2. So those x minus 2's cancel. So we have x plus 5 equals 7. Thank you. So I get x equals 2. But you should still go back and check. Okay, what happens if you check 2? Look at the denominator. Yeah, you get that 0 in the denominator. So does it work? No, it actually doesn't. So this one doesn't work when we check it. So it's no solution. So don't just assume because you factored that it's like, oh, I got rid of the bad solution. You did get rid of a bad solution, but the other one could be bad as well. Okay, and then sometimes it doesn't factor. So this next one I have x squared minus 2x plus 9 all over x plus 5 equals 3. Okay, and it doesn't factor. So in this case, you actually would have to do that longer method. You're going to take the denominator and you're going to multiply it to the other side. So we're going to have x squared minus 2x plus 9 equals 3 times x plus 5. Like that. So I have x squared minus 2x plus 9 equals 3x plus 15. And I get everything on one side. So some of you guys had trouble with this on the conic sections test because there was one problem where it was like x squared minus 2x equals 3. And then you guys were like, I don't know how to solve this. But you just get it on one side and you factor, right? Like it was like a panic moment on the test. Like, wait, what am I doing? All right, so on this one, I'm going to get everything on one side. So I have x squared. I'm going to have minus 5x. I'm going to subtract the 15 over. So 9 minus 15 is negative 6. And then I factor. So it factors into x minus 6 times x plus 1 because I need them to multiply to be that negative 6. So we get 6 and we get negative 1. So we still need to check. So how about this side of the room? So from Logan and Anna Catherine over, you guys check the 6. And the rest of you guys, you tried negative 1. Let's see if they work. Oh, I don't know why I did 12 there. 36. It's already moving on to the next one, wasn't I? 6 does work. So it all equals 3. Okay, and negative 1 does work. It does. So you have negative 1 squared plus 2 times negative 1 plus 9, and it does all equal 3. So they both work. So sometimes you can have 2 answers as well. Over. Okay, does this make sense? So this is solving equations that have rational expressions. Okay, so let's get to the weird stuff. So look at this problem. Doesn't this look so fun? This 9x squared minus 4 over x minus 2 divided by, woo-wee. So that's what it says in the notes. So it says sometimes we've seen crazy fractions within fractions. So these are called complex fractions. I don't know why they call them complex fractions. There are no complex numbers in them. I guess it's complex as in difficult. They're difficult fractions. Not really that hard. You guys can do these. No such thing, right? So a fraction, complex fraction contains one or more fractions, and its numerator, denominator, or both. So it says try simplifying the complex fraction. So if you have 1/2 divided by 3/5, so I just read that like this: 1/2 divided by 3/5. So the division sign with the 2 dots in the line. That's called an obelisk. That's simple. So I have 1/2 divided by 3/5. So we know how to do that. We just did that yesterday, right? So if I'm dividing by 3/5, what am I really doing? Multiplying by 5/3, right? So we're going to change it. So we're going to say, okay, well, I have 1/2, and I'm multiplying by 5 over 3. So when I get that, I get 5 over 6. So we do exactly the same thing with these ones. So we think of it as 2 separate fractions with a division sign in between them. So we're going to say, okay, well, I really have 9x minus 4 over x minus 2, and I'm dividing by 3x plus 2 over x squared minus 3x plus 2. So you guys did this on your homework that you started. So we're going to factor the 9x squared minus 4. So it's going to be 3x plus 2 times 3x minus 2 all over x minus 2. And then we're going to do times, so we're going to flip that second fraction. So the 3x plus 2 that was on the top before is now on the bottom. And that x squared minus 3x plus 2 is going to factor into x minus 2 and x minus 1. So we cancel any common factors, x minus 2, 3x plus 2, 3x plus 2. So it looks like our final answer would be 3x minus 2 times the quantity of x minus 1. And that's it. All right, so the next one's a little bit harder because now we have an addition or subtraction sign with the fractions, right? So it gets a little bit weird. So if I was going to do this one, I would do my 3 over x plus x over 2 in parentheses. And then we're dividing by x minus 1 over x. And we're going to get common denominators. Okay. So we're actually going to be talking about this in 9.2, getting common denominators. But what do you guys think? So sometimes I have to think about a number plugging in. And remember I said 7 is always a good number to plug in. So if I had 3 over 7 plus 7 over 2, how would I get common denominators there? 2 over 2 and 7 over 7, right? So that's what we're doing here. So I'm going to take my 3 over x and I'm going to multiply by 2 over 2. And I'm going to take my x over 2 and I'm going to multiply by x over x. Sorry, it's kind of hard to see there. That's x over x. So when I do, I get 6 over 2x plus x squared over 2x, all in parentheses. And then it was divided by the x minus 1 over x. So now that we have common denominators, so who can tell me, what do you think this is? 6 over 2x plus x squared over 2x. Yeah, 6 plus the x squared all over 2x. Not 4x, 2x, right? So keep those denominators the same. So we have 6 plus x squared all over 2x, right? Common denominators. Right? And then we do times, and we flip the second fraction. So I'm going to do x over x minus 1. So really the only thing that reduces out here are these x's. So x and x cancel. So we get 6 plus x squared, or x squared plus 6 if you want to write it that way, and then we have a 2 times x minus 1, and that's our answer. Okay. So there's actually a little bit of an easier way of doing this. So I can show you another shortcut, especially when you have like actual numbers. So let me go back up here. Well, I'll find some more room. You guys have a little bit of space underneath what you did. So let's say we had something and we had 1/2 plus 3/8 all over 5/4. So similar to what we just did, a fraction added to another fraction all over another fraction. If you are able to get the common denominator of all of those, so looking at the denominators, I have 2, 8, and 4. What would the common denominator of all of them be? 8. There's a quicker way of doing this. And this is just kind of a good skill to know in your math classes. We like clearing fractions, right? It's the way to clear fractions within fractions. So the least common denominator would be 8. So we multiply the entire numerator and the entire denominator by 8. That's allowed, right? We're multiplying the top and the bottom by 8, so it's like multiplying by 1. So when we do, we get 8 times 1/2 is 4. 8 times 3/8, what do we think? 3, right? 8 times 3 over 8. All over 8 times 5/4. Well, 8 times 5 over 4, what's that? Yeah, 40 over 4, which is 10. And right away we get 7 over 10. Done. That's an easier way of doing that. So on this other one, what would be our least common denominator for all of them? So if I have 3 over x plus x over 2 all over x minus 1 over x. Not just x though, be careful. So I agree x is part of it, but what else? A 2. So we're going to say 2x over 2x. And then we multiply that 2x into both things. So think about if I had 2x. So if I have 2x times 3 over x. 6x over x, right? And 6x over x is what? 6. So we get 6. And then if I have 2x times x over 2, 1 what? X squared. So I get 6 plus x squared all over. Now I have the 2x times x minus 1 over x. That's where our x's are going to cancel. So we're going to have 2 times x minus 1. So that's a faster way of doing that, and we'll do lots of things like that in this chapter. So we're going to be clearing fractions a lot, so we'll practice that concept. Okay, and the last little bit here. So it says warm up. So Bronwyn drives 50 miles at a rate of 60 miles per hour. On the return trip, she travels at 50 miles per hour. What is her average speed? Okay, so this is kind of a classic SAT question. These always used to be on the SAT back when I was in school. I don't know if they're still on there today. Maybe they are, I don't know. The SAT has changed pretty dramatically. All right, so it is always asked on standardized tests though. So the key to solving it is to find the total distance and the total time. So what do you guys think? So if she drives 50 miles at a rate of 60 miles per hour and then she travels 50 miles per hour on the way back, everybody always says the same number. What do you guys think it is? It's okay if you think it. the average speed. So what's her average speed if she went 60 miles per hour and then 50 miles per hour? 55, right? That's what everybody always thinks. It's not 55. Doesn't that blow your mind? You're like, wait, why is it not 55? She had this speed and then she had this speed, right? So here's what we're going to do. All right, so if she's going 50 miles per hour for 50 miles, you all know how long it took her to get there, right? 50 miles, going 50 miles every single hour. How many hours did it take her? It took her 1 hour. We get that, okay? So when we go there and back, the time that it took her was 1 hour. Because she was going 50 miles per hour for 50 miles. Okay. But the other one's a little bit tricky. So she was going 60 miles per hour. Does it take her more time or less time to get there? It takes her less time, right? So we need to think about what fraction of the hour it takes her. Yeah, so it gets a little tricky, doesn't it? So that's where I always think about the distance equals rate times time. If I'm trying to find the time, I'm taking the distance traveled divided by the rate. That's why this first one was 60 over 60, or not 60 over 60, 50 over 50, right? 50 miles at 50 miles per hour, and we ended up getting 1. So if we do that here, if I say the time is equal to the distance over the rate, the distance she went was 50 miles, and she went at a rate of 60 miles per hour. So it took her what fraction of an hour? 5/6 of an hour, right? Which makes sense, less than an hour. So when you're finding the average speed, what you're doing is finding the total distance that you went, and you're dividing by the total time that it took you. Oh, I was writing distance. I was speaking and writing at the same time. Total distance divided by the total time. Right, and that's, again, coming from this equation. If I'm solving for my rate, do you see how I divide by my time? So distance divided by time equals the rate. So in this case, our total distance, she went 50 miles there, she went 50 miles back. How many miles did she go? 100 miles total, right? So we'll write 50 plus 50, which is 100. And the total time it took her was not 2 hours, it was an hour and 50 minutes, right? So it took her 1 plus 5/6 of an hour. So we get 100 over 1 plus 5/6. So I'm going to combine those. So I'm going to have 6 over 6 plus 5 over 6. So we get 11 over 6. You could also do the 1 and 5/6 trick. 1 times 6 plus 5. Do you guys all remember that? So it's really 100 times 6 over 11, which becomes 600 over 11, which if I get my calculator out, 600 divided by 11 is 54.545454. So 54.54. It's almost 55, but it's not quite, right? If that was an answer on the SAT, you would have gotten it wrong. So tell me, why do you think that she's going slightly less than what you would expect? So her speed was slightly smaller than what we thought it was going to be. You're driving, when she was driving, how long was she driving the 50 miles per hour? How long did that take her? An hour. Was she spending more time driving slower or more time driving faster? Yeah, she spent an hour going at the slower speed, and she only spent 50 minutes driving at the faster speed. So it's not going to be directly half of that. She's going to spend more time going slower. So it's going to be slightly less than what you would think that average of 55 was, okay? Did you guys get it? Yeah. All right, so this is kind of the same thing. So it says Jared averages 3.6 feet per second when walking downhill on a mountain and 2.0 feet per second on the return trip when walking uphill. What is his average speed for the entire trip? Round to the nearest tenth. The only difference is we didn't say how far he was traveling. So you can let it be anything. You can say let x equal his total distance. Well, not total. We'll say distance, like the length of the trail. And we want to find the time that he spent going on each. So when he was going downhill, our time is equal to our distance divided by our rate. He went a distance of x, and he went a rate of 3.6 feet per second. But his uphill time, he's going slower, right? It makes sense that he would go slower. Its distance divided by rate is still the length of the trail x, and now he's going a little bit slower, 2.0. So what it does is it makes this complex fraction, because we take our total time and we divide by, or total distance and divide by our total time. Jeez, I keep writing time on top. Total distance, and we divide by our total time, right? Because we're thinking distance equals rate times time. So distance divided by time gives our average rate. So our total distance is he went x miles out, or feet out, and he went x feet back. So x plus x. And the total time was the x over 3.6 plus the x over 2.0. So it creates this complex fraction that we were just talking about how to solve. So it's up to you guys. You can solve this using that common denominator approach. Do you guys know what the common denominator would be? Any ideas? No? 3.6 and 2? You could do like 7.2. You just multiply them together always, right? Or you can combine, and so you can say, okay, well this one's going to be, let me write it on the next step. So I have x plus x, which is 2x. And then I have x over 3.6, and we have x over 2.0. So we're going to multiply by 2.0 over 2.0, and we're going to multiply by 3.6 over 3.6. So we get 2x over 2.0x plus 3.6x all over their common denominator of 7.2. So it gets a little messy. So we have 2x over 5.6x over 7.2, and it ends up, it seems weird, but the x's don't even matter. It didn't matter how long he was traveling on that trail. Because when we multiply by the reciprocal, oops, running out of room. If I have 2x and I multiply by 7.2 over 5.6x, those x's will cancel. So it didn't matter how long that trail was. So we get 2 times 7.2, so 14.4, and we divide by 5.6. And his average speed ends up being 2.571. What was that, feet per second? So it is between those numbers, but the average of those two numbers, if I just added 3.6 and 2 and divided by 2, was 2.8. So see how it's slightly less than the 2.8 because he's spending more time walking at a slower rate. Okay, you guys get it? That's a hard one. That would be like a bonus question on your test. That's why I have like challenge next to it. All right, so let's stop there.